This program is brought to you by the University of California, Davis on iTunes U. For more information, please visit us at itunes.ucdavis.edu.
Okay, welcome everyone. Tonight is lecture number 10. It's about half point, I believe. And we are right now at one of the most fundamental concepts of this whole business of geometric modeling, the topic being splines. Right? You know everything about splines already, right? You are laughing. You know everything that I talk about is in the book, right? So you just read the book in the matter of the first week of the course and you know everything, right? I just tell you stories, right? I just explain this material a little bit differently. I try to help you view it differently. Or try to help you understand what the process is leading to the results and recipes that are described in the book. So, splines. The most important concepts about this splining business is a concept of blending things together in a continuous way. That is the most important aspect. How do I build a complicated geometry, be it a curve or be it a surface, from multiple pieces, very simple building blocks, quadratics or cubics, at most, or typically at most, and ensure that these pieces come together in a smooth, continuous way. Positionally continuous, derivative continuous, curvature continuous, and other forms of continuity. Now, let's go back then again and understand what it means to extend a quadratic curve or a cubic curve in a continuous fashion to the right. That's the essential building block. Okay? The goal for today will be to understand the derivation of a cubic spline. You've heard this word, but cubic spline, the cubic spline is the most important building block for many, many computer-aided design systems. So that's the goal for today, to drive towards that goal. And again, the most important part is to understand the concept of continuity, right? Continuity is the most important concept here. And I will explain it again by two concrete examples. C1, continuity. You have some of this already in your notes, but I just want to repeat it because it's so important. In C1 continuity, if I just do it for the example of a quadratic curve, a quadratic Bezier curve. If I have a quadratic Bezier curve, okay, and I have my timeline, my parameter t, and I have a first curve defined by that polygon, both 3 points, and by this interval, which has a particular length, call it alpha. And then I want to extend this quadratic curve in a C1 continuous fashion. That means I want to preserve the derivative when I extend the curve or continue the curve. So the second curve will be defined over this part of the t-line, and I call that length alpha. So there is a ratio here, alpha to beta. What do I have to do? These are the control points of the first curve, B0, B1, B2. And I want to extend it continuously by preserving the same position at the endpoints and by preserving the same derivative, first derivative behavior. And what we learned was, well, then the first control point of the second curve has to be that one. And then I have to put the next Bezier control point on this line. And I have to preserve a certain ratio, namely this ratio, alpha to beta. And so here I have this next control point. And I split this line segment in a ratio alpha to beta. And then the next point, the next Bezier point of the second segment is free. I can place it anywhere. The location of this point has no influence on the continuity there, the C1 continuity. So then this B0, this is also B0 bar, control points of the second curve, have this bar on top. So B0 bar, B1 bar, B2 bar. And this one is free. You can move it. It has no influence on the C1 continuity at this breakpoint. Right, so there. 2 segments, 2 domain intervals, a certain ratio down here, and that ratio maps up there. That's the important piece to remember for C1 continuity. Then that was A, so B has to be about C2 continuity. C2 continuity. And this will be the fundamental concept for the cubic spline. So let me start with a cubic curve on the left. So here I choose to have 4 control points, B0, B1, B2, and B3. And again, I want to have 2 curves defined over the T-line. The first one here, the second one there. Again, these 2 domains will become these deformed curves. Here's the first one, and this piece of the line will get deformed and will become the second curve. Again, we have a ratio alpha to beta here. And if I want to extend this cubic curve in a C2 continuous fashion, again, I have to map these ratios somewhere. So first, of course, the second curve has to start where the first curve ends. That is the first control point. Then I have to map the alpha to beta ratio onto this line segment, just like in the case I had on the board before. So this is, again, a ratio alpha to beta. And now for the next curve to have a C2 continuous transition here, I also have to map these ratios further onto this line. Okay, so here is also this alpha to beta ratio. And I get this helper point. And then I have to also construct a line going through these 2 points and map the ratio alpha to beta also there. And then this point will be the third Bezier point of the second cubic, and the last one is free, can go anywhere. Okay. So in this case, I wanted to connect 2 cubics. Okay. Connecting 2 cubics, connecting 2 cubic Bezier curves. And so B3 is identical with B0 bar. This one is B1 bar. This one is B2 bar. And this last guy is free. B3 bar is a degree of freedom. You can put it anywhere. So then this first curve gets extended like that. Okay? And so the important part is that these 2 curves come together, sharing the same position, the same first derivative, and the same second derivative at that point. So, and for reasons that will become obvious later, I call these helper points D points. Okay? The helper points are D points. This is the essential building block for a cubic spline. Why? Because this configuration here tells you what geometry has to be satisfied to join 1, 2 cubic curves in a C2 fashion. That's what I want. In a sense, that is also related to the natural spline, the spline that has minimal energy in it, and so forth. This is a configuration that we really have to digest and memorize. Okay, everything that, or much that follows, will be based on just that simple configuration. Okay. Okay. Now to the ideas. The problem we are aiming at is the following. Don't copy it, just motivation. A user will click a bunch of points, and you want to interpolate these points with one of those very smooth spline curves, okay, using cubic segments passing through each pair. Okay, so you want to get a curve that looks like that. Okay, and each one of those segments should be a cubic segment. So each one has its own independent 4 local control points, B0, B1, B2, B3 for this segment, right? B0, B1, B2, B3 for that segment, and so forth. The question is, how do you obtain the circles, the Bezier control points, from the original points to be interpolated? That's what I'm driving at. So I say towards the cubic spline. And again, I want to put this one example on the board that I had on the board last time, because that, again, the configuration that we really have to digest and fully appreciate. I say this is the geometrical configuration for a C2 continuous cubic spline. This is the configuration of a C2 continuous cubic spline. And so I think I had this configuration there. 1, 2, 3, 4, 5. And so these points on this polygon, I call them square. And then I will roughly split these line segments in thirds. Connect points on these original line segments in this way. And split these next generation of line segments somewhere close to the midpoint. And these will be the points that are the original points to be interpolated. Okay. So that configuration you have to appreciate and understand. And where are the Bezier points? Here's the Bezier point, here's one, here's one, and here's one. So those 4 Bezier points define the first cubic curve. So the first cubic curve, or the first segment, is that guy. The next one, of course, is this defined by that Bezier point, this one, and this one. So again, 4 Bezier points. We never go beyond that for each segment. Very simple. Cubic building blocks. So here's another cubic building block. And the last one is here. Bezier point, Bezier point, Bezier point, Bezier point. That is a control polygon, and here's our happy curve. So we have a cubic spline curve that consists of 3 segments, which are all merged at these breakpoints in a C2 continuous fashion, according to the picture over there. This configuration that you see over there in that other picture is the same kind of configuration that you see here. Now, where are the deltas? So I didn't talk about that. So, of course, everything is defined over this parameter line. And I do make the switch to calling this line now U. Don't worry about it. And so what do I need? I have 3 segments. That means I need 3 relevant, I call them relevant parameter intervals. Right? 3 segments means 3 intervals that get deformed or bent into the pieces of the curve, first, second, third. And I call them U0, U1, U2, and U3. All right? And for reasons not quite obvious to you yet, I extend this list of the knots they are called. These are called the knots. I expand this by 2 to the left and 2 to the right. So there is another one, which I put here. And I call it U4. There's another one I place here. And I call that guy U5. And correspondingly, I add 2 here to the left. And I call that guy U minus 1. And here is U minus 2. Okay, so now I put the ratios on top. The ratios are, here is my delta minus 2, here is my delta minus 1, here is my delta 0, here is my delta 1, delta 2, delta 3, and delta 4. So those are the individual length of these intervals. I said we have to preserve certain of these ratios given by those intervals in this configuration. Where are they? Everything is by pattern. Okay, and you will easily see how certain indices over there map to parts of this polygonal configuration. Well, let's just do it. I start with delta minus 2, so put it here, right? Delta minus 2 to delta minus 1 to delta 0 is the first way I split that line segment. The next one then has to be delta minus 1 to delta 0 to delta 1. So the next one has to be delta 0 to delta 1 to delta 2. The next one has to be delta 1 to delta 2 to delta 3. And the last one will be delta 3 to delta 4 to delta 5. Oh, what was it? 2, 3, 4. Delta 2, delta 3, and delta 4. And that's it. And we have to preserve certain ratios here where the curves come together. So the first one here is the first curve coming together with the second. So that is delta 0 to delta 1. Must be preserved here. Delta 0 to delta 1. So this one then must be delta minus 1 to delta 0. This one must be delta 1 to delta 2. And this ratio must be delta 2 to delta 3. Okay, just by pattern. Now I can give these things names. And again, I have to say this is a solution to the problem. What is the problem? The problem is I give you the 4 bullets, and I want to compute the circles, right? The Bezier points for each segment. But I do that indirectly by computing the squares, and from the squares I can compute the circles. Anyway, so these are the original points. I call them P. So this would be P0, this is P1, this is P2, and this is P3. So I stay away from the number at the variable n and make it concrete with extra numbers. So P0, I also count the Bezier points I get. I just start at 0 and go all the way to whatever the highest index is. So this is Bezier point B0, this is Bezier point B1, this is Bezier point B2, this is Bezier point B3, this is Bezier point B4. I keep on counting. B4, this is B5, this one is B6, this one will be B7, B8, here this guy is B9, and that's it. So this configuration is a configuration of a C2 continuous spline consisting of 3 cubic segments. It's the answer to a problem. The problem we want to solve goes the other way. The problem we want to solve is this. I give you the original points, and I give you this arrangement of knots. Please compute for me, computer, the squares of this outer polygon and from the squares, compute the circles. And all of that is obviously implied by these delta ratios. And that's what we have to write down. Right? This is just a figure, and the figure now becomes algebra. What do we have to understand here? What is the critical part? We only need to understand what happens where two pieces come together, because it's the same everywhere, right? We only have to understand in detail what this relationship is locally. For example, if you understand what the relationship here is in this figure between that square and that square and that square, and this point and the Bezier circles here in this local neighborhood, you only have to write down that once, because the same set of constraints applies all over the place, just with shifted indices, right? It's always the same configuration, the same constraint that apply all over the place. We only have to understand it for one local part of that. So why don't we just do that? We write down what is going on locally. So this is now not idea. This is really the essential building block for the cubic spline. Local, this is a very important figure. Local cubic spline conditions. Cubic spline conditions. Maybe the most important picture for the whole class. Local cubic spline conditions. I only want to understand what's going on in a local neighborhood. I want to understand what's going on here in the neighborhood of 3 of those squares from the former figure. And, okay, what is going on there? I also said there is this additional line here. And here's an original point. Okay, here's an original point. And so then there are these Bezier points. Here's a Bezier point. This guy, the original point, is a Bezier point. Here are 2 Bezier points on this. And there are 2 Bezier points somewhere here. Right, this is just an excerpt of that figure in the middle. Now I give these guys some names. And I name them with a varying index I. So that applies everywhere. This is my point, my given point, pi. Okay, one of them. Okay, so pi has a corresponding square, and now I call this guy di. Okay, I call this di. If that guy is called di, this guy is called di plus 1. This guy must have as its name di minus 1. And what else? I have to understand something about the parameter side of the things. So there is my U line, and there are 2 curves coming together here, right? Or 2 curve segments. There's the first segment to the left, and the second segment there to the right. The left one is defined over the interval from I minus 1 to I, and the second one is defined from I to I plus 1, right? To understand that, so I put these 2 intervals down here. So pi corresponds to ui, right? That's an easy correspondence. And then here is my ui plus 1. Here is my ui minus 1. Here is my ui minus 2. And here is my ui plus 2. Okay. And what is locally of relevance? Again, the correspondence is made here. Ui corresponds to pi. Okay. This interval becomes that curve, and this interval becomes that curve. Right, that is the correspondence, but I do not care so much about that. I care about the length of these intervals here, and I give them names. So this guy is ui minus 2, so the delta on top of it is delta I minus 2. This delta must be delta I minus 1. This one is delta I. This is delta I plus 1. Okay, the length of these respective intervals on the u line. Where do they map? Well, they map in certain ratios onto this polygonal configuration. This configuration, delta I minus 1 to delta I, maps here. So here I have the ratio delta I minus 1 to delta I. Okay, then what ratios do I have here? Here I have the ratio of these three intervals, and I called them delta I minus 2 to delta I minus 1 to delta I. And then the ratio I have here must be delta I minus 1 to delta I plus 1. Okay. What am I after? Given is only the bullet point, P. Right? That point is given. From that point and all its other neighboring bullet points plus this not set, I want to compute the squares. And from the squares, I can get the circles. When I have the circles, I have the definition of each cubic segment. So how do I do that? Well, I just have to write down what all of this means. Right? How do I formally, algebraically write this condition down? This is a picture. When there is a good picture, you can also tell the story algebraically. And you just write it down in the language of algebra. And as I said before, the only algebraic building block, interpolation building block you really need to understand in this class is linear interpolation. Everything is linear interpolation and nothing more. So, side note, I should put this here. So this is just remember. Okay. Again, this is the essential formula for the whole class. I have a line. I have two endpoints. And I have a point on it, that guy. I call this point A, I call this point B, and this arbitrary point there I call point C. Okay, and now I look at certain ratios or length. I can say this is of length alpha, and this is beta. Then how can I express C in terms of A and B and this ratio of length? That's the most important building block. It's always C expressed. It's a combination of A plus something times B. That's right. That's linear interpolation. Something is a linear combination of two other primitives, A and B. And I always have to divide or normalize by the total length. So I divide by alpha plus beta. Total length, alpha plus beta. Okay, and now always remember that the left point, A gets multiplied by the right length, beta, okay? So the first point, A, gets as its weight, beta, and the right point, B, gets the weight alpha, okay? So this is, just for us to remember, linear interpolation, the most important building block that we now apply for the figure I have on the board, all over the place. Okay, just have to understand this again. Expressing a point on a line segment in terms of its two defining points, take the point, determine where it lies along this line, look at these partial length, and then write it down like this, in this form of the linear interpolation formula. And this is what we will do now on this picture. What will I do? I want to express this point Pi in terms of its left and right neighbor. That's where I start. Okay? This is my point C over there, and this is my point A, and this is my point B, right? That's where I start. And then I will write down all these other circles in terms of their squares. Okay? All right, so I call this point my A point, and I call this my B point. These are just helper points for the time being. And my first formula I will write down is writing pi in terms of A and B and these two length ratios. Okay, so this is the derivation of the linear system of equations, linear system of equations defining the control points and the control points here are those squares, defining the control points square of a cubic spline. So that's what I'm after. And so this is my important figure, fig. Okay. According to fig, the following conditions hold. Okay, let's see. 1. Pi equals something times A plus something times B. Something times A plus something times B. Okay, what are the ratios in front of it? I have to normalize by the total length of this, delta I minus 1 plus delta I, divide by delta I minus 1 plus delta I, divide by delta I minus 1 plus delta I. And then in the numerators, left point gets multiplied by the right weight, delta I. So delta I goes here, and delta I minus 1 goes here. Okay. I do not like to have to carry this expression around all over the place, so I multiply both sides by this delta I minus 1 plus delta I. Okay, so I only have it once. So I change this, and I change it to the form delta I minus 1 plus delta I times pi equals delta I times A plus delta I minus 1 times B. Okay. Now I want to substitute for A and B. What is A and B? What are these A and B points? These were just helper points. Okay? B is between a di and a di plus 1. Those are the points I'm after. Okay? And point A is a combination of di minus 1 and di. Okay, so I write it down what A is in terms of di minus 1 and di, and I write down what B is in terms of di and di plus 1. Okay, so 2. I write down an expression for A. What is A? A is what? A is a combination of di minus 1 plus something times di. What goes in front of those? Well, the total length of this line, which is delta I minus 2 plus delta I minus 1 plus delta I, So I divide by delta I minus 2 plus delta I minus 1 plus delta I minus 2 plus delta I minus 1 plus delta I. And the left point gets multiplied by the right weight. This point is a combination of that and that. So the left point gets multiplied by this, which is delta I. So delta I goes here. And the right point, di, gets multiplied by the left chunk of the segment, which is delta I minus 2 plus delta I minus 1. Delta I minus 2 plus delta I minus 1. Okay, now I do the same thing for b. I can express b similarly. And I say this helper point b is a combination of di times something plus di plus 1 times something. What is something? I have to divide by the total length of that line segment, di minus 1 plus di plus 1. Okay, so delta I minus 1 plus delta I plus 1. Delta I minus 1 plus delta I plus 1. Okay, left point gets multiplied by the right length, which is delta I plus 1. Delta I plus 1. And the right point gets multiplied by the left segment, which is delta I minus 1. Delta I minus 1. Okay, so now I have my expressions for A and for B, and I can plug those into that equation. Okay, and then I will have an equation that only relates the deltas and the p's to the d's. That's what I want. All right, now I can take this, and I call this star star, and I call this star. And now I can do in step 3, I can insert these expressions into star. And then I get the linear system of equations. All right, next thing is 3. Insert star star into star. Okay, what do you get? Okay, now you have to help me because I will be doing all kinds of problems if you don't watch me. So I have delta I times that guy, right? Delta I times that guy. Delta I times delta I is delta I squared, right? So I have a delta I squared times that. So, and on the left side I have that point I times something. So I have delta I minus 1 plus delta I times a point pi is something times di minus 1. Okay. Okay. It's delta I times delta I is delta I squared. Delta I squared divided by delta I minus 2 plus delta I minus 1 plus delta I. Okay. All right. All right, now comes this di thing, right? Let's see what we have to do there. Plus, now comes something else. Delta I times a. Okay. We plug a in there. So it's delta I times this expression, right? Delta I times this term. So it's delta I times that stuff Okay. So plus delta I times delta I minus 2 plus delta I minus 1 divided by this delta I minus 2 plus delta I minus 1 plus delta I times di, but there's another di term here coming up, right? So I can put it together, plus delta I minus 1 times b. Okay, so delta I minus 1 times this stuff, so it is plus something, and I divide by now this delta I minus 1 plus delta I, divide by delta I minus 1 plus delta I plus delta I plus 1, closing bracket, times what? It was delta I minus 1 times that. Delta I minus 1, delta I minus 1 times delta I plus delta I plus 1. Delta I plus delta I plus 1. And what is that? Times di. Times di. All right, and now the last term is delta I minus 1 times b, this part. Delta I minus 1 times delta I minus 1 is delta I minus 1 squared. So plus something times di plus 1. And it was delta I minus 1 squared divided by that. Delta I minus 1, delta I minus 1 plus delta I plus delta I plus 1. So that's it. And this is a grand solution here. Well, not the solution. This is just one equation, right? Is it all correct? The original point pi is expressed in terms of three other points, the d points, di minus 1, di plus 1. First one is multiplied by di squared over I minus 2, I minus 1i, correct. Last one is di minus 1 squared, correct, over I minus 1i plus 1, correct. And the other one swap, di minus 1, I minus 2, I minus 1, I plus 1, correct. And then, all right. So that's the correct formula. When you think about this, there's a pattern involved too. You only need to think in terms of patterns to verify all of that. So, and this equation, how many of these equations do we have? How many equations? This is a point I. This is the equation for an arbitrary point I. How many I runs from where to where? 0, p0 up to pn. Huh? So I from 0 to n. Okay. So then I could write all these equations underneath each other, right? What do you get then when you write all these equations under each other? Then you get, that's where you get the linear system of equations. The given things are the points, the pi's. The unknown things that you need to compute are the d points, which you don't have. But once you have the d, when you have the d points, you get the b's, right? The circles. Okay. So now we have to compute the d. How do you get the d's? Solve the linear system of equations, right? And we all remember that. So let me just do that. Put this on the board in a more obvious way. Okay, so this is your linear system of equations. Linear system. For what? For the d's, right? For the d's. Or, in abbreviated form. What do you have? You have something times the point is something times a left d plus something times a middle d plus something times a right d. That's it, right? That's the structure. Something times a given point equals a linear combination of three d points with certain ratios in front of them. So I can just give these guys names. Okay, these things are ugly. We cannot memorize them. So we just say the system you have there looks like this. So you have an alpha I times a di minus 1 plus a beta I times a di plus some gamma I times d point di plus 1 equals some kind of, call it weight, whatever, call it weight times the point pi. Okay? This is the essential structure of that equation, right? There's a bunch of complicated coefficients in front of the d points equal the original point times some factor. That's it. This is just condensed. Okay. And so again, this is for I from 0 to n, right? Given our the points p0 up to pn. Now I can make it even more obvious to show you that this is a linear system by just putting the linear system on the board. Okay, so now I just say in linear system form or in matrix form, right? In matrix form, what is this? Well, you have a coefficient matrix with these alpha, betas, and gammas in there. The unknown vector is a bunch of d's, and on the right-hand side you have the points you want to interpolate. So what do you have? You have a matrix. Then the matrix is times the unknowns. The unknowns are the d points equals something on the right-hand side. Okay. How many equations do we have in total? N plus 1 equations, okay? N plus 1 equations. So the first equation we get when we plug in I equals 0, right? When we plug in I equals 0, we say alpha 0 times d minus 1 plus beta 0 times d0 plus gamma 0 times d1 equals something times 0.0. Okay, so we write this down. Okay, so the first equation we have is alpha 0, beta 0, gamma 0. Right? And they multiply the first three control points. So that is d minus 1, d0, and d1. Equals what? Equals weight I, right? Weight 0 times point I, 0.0. So equals weight 0 times 0.0. Okay. Correct? It's just the matrix notation of that equation, right? Alpha 0 times d minus 1 plus beta 0 times d0 plus gamma 0 times d1 equals weight 0 times 0.0. Okay? Now I can write all these equations down in matrix form, fill up this matrix, and the last equation I get is for I equals n. So what does that mean? Well, I set I equals n, and I get the expression alpha n, beta n, gamma n. Okay, and they go along with the d points, dn minus 1, dn, and dn plus 1. Right? So dn plus 1, dn, and dn minus 1. Okay, dn minus 1, dn, dn plus 1. All right. What is that on the right-hand side? On the right-hand side, I get Wn times Pn. So Wn times Pn. All right. Okay. All right. So this is a special type of matrix. Each row in this matrix has how many entries, really? Only 3. The rest is all 0. Okay. So there are these 3. There's the diagonal and the 2 off-diagonals, and those are the only ones which have entries different from 0. It's a special matrix. It's called a tridiagonal matrix. Okay. So this guy is called a tridiagonal matrix. Tridiagonal matrix. And that is a beautiful matrix. Okay. All right. Do you see something, or what is going on here? What doesn't quite mesh? Very good, very good. I took care of that already, right? When I set this up and put it on the board, right? I was foreseeing that, right? You see that? How many points do I interpolate? N plus 1, from P0 up to Pn. That means I have n plus 1 equations for how many d's? The d's go from, here's d0 up to dn. Okay, they correspond to P0 and Pn, but I have 2 additional ones. I have this guy to worry about, the d minus 1, and I have to worry about this guy, dn plus 1. Okay, I have 2 more unknowns, then I have elements on the right-hand side. What does this mean? When I have 2 degrees of freedom, then I'm free to choose them anyway. That means I could say 1 times this thing equals something. I can just set it. Okay? You just set it. The user sets it. So you just say, for example, you just say the user says that d minus 1 times d1 equals something. Okay? Say that is some value, call it a. Okay? Some number. And the same at the end. This is the degree of freedom. The user can play with it. You can say at the end, 1 times dn plus 1 equals some number, b. Okay? So I can say these are user specified. Okay? User specified, they are called end conditions. So 2 user specified end conditions. Or one can think of them as end conditions. We come to that later. So this is all 0. This is all 0. And all this is 0 and this is 0. Okay. So now you have a system that consists of n plus 3 rows and n plus 3 columns for n plus 3 unknowns, and you are happy, right? So this is now what? It's an n by 3, n plus 3 by n plus 3 matrix. And you are happy because now you have n plus 3 unknowns, d, and n plus 3 elements for the right-hand side vector. Okay. Should leave this there. Do I need this? Actually, what you have on the board is very fundamental, very important stuff. What do we do now? What do we do? Yep. What next? What do we do with this? let's go back to our problem, okay? The most trivial problem is this. I give you 2 points and the two end conditions, these two d's at the end, the d minus 1 and the dn plus 1, right? That's the most trivial one. So I can say, well, here is another, I specify this d point and maybe this d point. Okay, that's the input. And I also specify some deltas down there. I need 5 in this case, 5 deltas, 6 u's. So here's my d minus 1 that I specify. This is my point 0. This is my point 1. This is my d0, d1, d2. This must be my d2. This is all I specify. From that, I want to construct my cubic curve. Okay, something like that. Don't know how it will turn out. These are the two unknowns, right? d0, d1. Okay, once I have that, then I have my Bezier points, these guys, and I have my one single cubic curve. That's the simplest case. User specified 2 points and 2 end conditions. This was an end condition, and this is an end condition. 2 unknowns, really only. This, that. The system that has to be solved in this simplest case is like this, right? 1 times here are 4 d's equals something, and then here are 2 equations. And there's the 1. Okay. 4 by 4 system. Okay, so I have to deal with this system. How do I deal with this system? Do you know how to deal with it? I say tridiagonal matrix. Is this good that we have a tridiagonal matrix, or? It is very good, right? Why? Yes. How fast is that one? Order n, right. You need to invert this matrix to solve for the unknown d's, right? Matrix inverse takes this matrix inverse times unknown vector equals matrix inverse times right-hand side, right? So then it becomes a unit matrix, and you only have the unknown d's on the left-hand side left over, and on the right-hand side you have the solution, right? Matrix inverse times the right-hand side stuff. So, but you do not really need to invert this thing. There's a tridiagonal solver that does a bunch of steps of forward and backward substitutions, and you can actually obtain the solutions for the d's in linear time. It's very, very good. Why is it very good? If you deal with a full-blown matrix where you do not have a nice structure like this, how long does it take in general when you have an arbitrary full-blown matrix? N cubed. Okay? N cubed. N cubed. Interpolating 1,000 points is probably not a lot anymore, right? You can think of scanners, right, which scan 50,000 points from my hand, 100,000 points from my hand, right? So that you easily run into the problem of having to interpolate thousands of points, huh? Easily. So if you have I talk surface case here, right? Similar. You also end up with matrices in the end for the surfaces. So 1,000, and then you have 1,000 by 1,000 matrix, and it requires order of 1,000 cubed. 1,000 cubed is a billion, right? Order of 1 billion time units to invert that thing. It's a lot of time. It's a lot of time. It's 1 million times more time than is needed if you can deal with 1,000 by 1,000 matrix in order n time, because it's tridiagonal, the matrix, right? So that's very good. So we are very happy that this problem is formulated in such a way that you only have 3 diagonals where you have the non-zero entries. Okay? So can use tridiagonal linear system solver, linear system solver to compute compute the Ds. Okay, tri-diagonal system solver. Where do you find such a thing? Probably on the web somewhere, right? Public domain software, tri-diagonal system. You find it, right? Get one. Okay. Get one. And then you have wonderful order n time complexity for computing your Ds. What else? I think I should give you a special case. I should give you the special case for this matrix when people use a very simple setting for the knots, namely uniform knots, 0, 1, 2, 3, 4, 5, 6, 7. Okay? Then this becomes even more simple, because then these numbers are very simple. So I should give you that. That's also a good debugging tool, because when you go home and you actually code this up, you will make mistakes. Right? Why will you make mistakes? Because you have a bunch of indices floating around all over space, and you don't see the pattern yet, right? So it will be hard for you to debug, to see which index of those indices is wrong. Maybe there's even a wrong index on the board, right? But definitely once you code it up, you will be off by 1 or 2, whatever. Should. It's up to you. A chord length parameterization is in general good. A centripetal parameterization is oftentimes better. If you want to improve it further, you go towards an arc length parameterization, and you actually consider the length of the actual arcs that come out. And then you iterate on that, and you improve the sequence of knots over and over until they are no longer improvable. Okay. So yes, I mean, the best parameterization is a parameterization where the length of the line segment is the length of the arc, the curved arc. That's the best one. Okay. In a sense, it's very hard to come by, because here you have the other problem. You have points, you don't know how long the arc is. So the best approximation you have for the arc length, which is to be constructed, is to consider the chord. Okay, that's the chord length. Okay, but once you compute the first interpolating curve, then you have actually an arc, and then you can compute its length. And then you can adjust the parameter values and then do it again. Okay. So yes, the best is the arc length, followed by centripetal. These are rules of thumb. Okay. Arc length, centripetal, chord length, and then comes uniform. Uniform is very bad. Okay, uniform is only good if the spacing of the points is uniform as well. But if you have a highly non-uniform spacing, a lot of points here, no points here at all, and then a lot of points there, then you should not do uniform, because it doesn't reflect the spacing. So parameterization is good if the spacing of the knots reflects the distribution and density of the points. So now a special case for this, okay? And this is a good case to test when you set all your u sub I values to I. U sub I equals I, you get a very special matrix. And I'll just give you that. Special case. Special case. Special case. Okay. Special case is u sub I equals I. Okay. And I goes from u0 is 0.0, but we go 2 to the left. I from -2 up to point n is n, up to n plus 2, right? N plus 2. In this case, the matrix takes on a special form. Linear system looks like this. S1, dn plus 1, something like this, something like that. What is going on? Okay. If the spacing is always 1, then all these deltas are 1, right? All the deltas are 1 in that case. All deltas are 1. Right? Because the delta is always the distance between two consecutive nodes. So you can plug 1 in there for each occurring delta, and then you get the special case. Right? So this means all delta I are 1, right? And that's the special case. Okay, so you divide by 3 here. 1 plus 1 plus 1 is 3. And then here you have 1 plus 1 is 2. So you multiply that over. There's 3 times 2 gives 6. So on the right-hand side, you probably have something like 6 times something. Okay. And what is left over here? Here's the delta is 1, so the 1 squared is 1. So there is a 1 times something. And here you have 1 times 1 plus 1. 1 times 1, 1 times 2 is 2. 2/3 that went over. 2 plus 2 is 4. 4. 1, 1, 4, 1. This is right. 1 again. 1, 4, 1. You see the 1, 4, 1 pattern all over. 1, 4, 1. 1, 4, 1. 1, 4, 1. Here is your 1 diagonal, your 4 diagonal, your 1 diagonal. All right. Should be what? That was 6 times the points, right? Here is point 0, and here is point n. That's the structure. And we still have to worry about these end conditions. What to do with these degrees of freedom? Okay. And I want to talk about that just briefly, how we get a handle on these degrees of freedoms at the end. We have 2 degrees of freedom, 2 more unknowns, then we have points to be interpolated, so we can use those 2 additional d points to specify something at the ends. Okay, so what do we specify? We have all the points, boom, 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 n plus 1 points, and we have 2 additional degrees of freedom, right? What makes sense to specify? We have 1 curve, we have 2 ends, we have 2 degrees of freedom. What can we specify at the ends that makes sense? Give me anything. We specify the endpoints plus the end vectors. Makes sense, right? We have just enough degrees of freedom left to specify that. So the system tells us we can specify here something in this row and in this row. So what we do, we specify the n plus 1 points, right? Points P0 up to Pn, plus we specify the derivative vectors at the end. And 2 derivatives. Okay, and I call them P naught dot, or P naught bar, and P1 bar. Okay, those are the derivatives here. Can do that. So that means I specify my points. Pn bar, absolutely right. I specify my points. And I have 2 degrees of freedom. And I specify how this curve should start in terms of derivative vector or velocity vector, and how it should end. With this information, everything is uniquely determined. It's beautiful. Okay? All the points plus 2 vectors, and everything comes out uniquely defined. So you get the unique spline that will look like that. And yes, you could rotate this guy around and change it and make it go in any direction, and you get still a unique answer. Okay. How you choose it is another question. Okay, so we need to come up then with a way to specify these first and last rows to define the relationship between the derivative and the d points. Okay, so two additional equations defined by specifying the derivative vector at the ends, by specifying derivative vectors at the ends. Okay, and again, we only need to understand the configuration at one of the ends. The other one follows by symmetry. So I will draw a picture. You always should start with a picture. Okay, when you don't understand something, just draw a picture first. The picture tells you the geometry. From the geometry follows the algebra. From the algebra follows the computer program, right? So at least I think that way. Some people don't need the picture. I've seen textbooks. There's not a single picture in a textbook, right? Know those textbooks? Yeah, textbook 500, 600. There's not a single picture in there. Some people like to just think algebraically. I can't do it. I like pictures. That's why we're in graphics, right? I like pictures. So the situation at the beginning, okay? All right. So what is going on at the beginning? At the beginning, we have this configuration. We have the first point, the first d point, which is called d minus 1, right? D minus 1, this is d0, and this is d1. Okay, so the curve starts out here somehow, and here's my first point, my point p0. And I would specify the derivative there. So I specify the point plus some derivative vector, right? I call that p0 bar. And so what is the situation there? Here's my u line. Point 0 corresponds to u0, right? u0, and I have these additional ones to the left, u minus 2 and u minus 1. And I have my delta minus 2 here, my delta minus 1, and here is u1, and here is my delta, 0. That's the local configuration. So this is how the curve starts out for this first segment, right? And I want a relationship that establishes the relationship between these d points and these guys. Okay, so I remember this, that here this was d minus 2 to d minus 1 to d0, right? And this was d minus 1 to d0. And then this is a cubic Bezier curve, right? A cubic Bezier curve, and I can write down what its derivative is in terms of its control points and all of that. Right? I can go back to the formula, and I can write down this point, right? Let me write down this point here, this point A. Okay. What is the derivative of a cubic Bezier curve? To remember that. So that was the derivative p0 bar is related to something like 3 divided by, I go left now, delta minus 1 times p0 minus a. p0 minus a. I'm not quite happy with that. I need to express a in terms of these two d's, because that's what I want, the two d's. So what is a? So the remark, what is a? A is this combination of the d minus 1 point plus something times the d0 point. Okay, what is to be divided by d minus 1, d minus d minus 2, d minus 1, d0, delta minus 2 plus delta minus 1 plus delta 0, delta minus 2 plus delta minus 1 plus delta 0. And then A is this point. Left point gets multiplied by right by delta 0. And right gets multiplied by the left chunk, delta minus 2 plus delta minus 1. Okay. So that's what I have there. Now I rearrange the thing a little bit and bring this over on the other side. So I have delta minus 1 divided by 3 p0 bar equals p naught minus a. Okay, I don't like this either. I want to have the a on one side, so I bring a over as positive. So I have a equals p naught minus this part minus delta minus 1 over 3 times p 0 bar. Okay. Now I have on the left-hand side my unknown d's. Okay, I spell it out. This expression for the a's, right? It goes here. So now I have delta 0 over delta minus 2 plus delta minus 1 plus delta 0 times d minus 1 plus delta minus 2 plus delta minus 1 over delta minus 2 plus delta minus 1 plus delta 0 times d0 equals this stuff, equals p0 minus delta minus 1 over 3 p0 bar, the derivative there. Okay, so this is one of these helper equations for one of the two ends, namely the beginning, right? It's a linear equation that relates d minus 1 and d0 to the point 0 and its derivative there. Okay, so that's the additional equation for the first line. Of course, I have to multiply that guy a little bit, etc., etc. Once I insert it into this form of this special case, I want to give you the solution for that special case. So in that case, this entry becomes 1. This becomes 2. How beautiful, right? It's kind of like half of the equation, so 1, 2. And here it is 2, 1. Huh? And then on the right-hand side, it turns out, when you actually multiply that out, it is p0 over 2 minus p0 bar, its derivative, divided by 6. That is the first number there. And the last number in this column vector then becomes pn over 2, pn over 2 plus, not minus, plus pn bar, its derivative, pn bar over 6. A very beautiful coefficient matrix, right? Very beautiful. 1, 2, and then all the other entries are 1, 4, 1, 1, 4, 1. Here are your unknowns. And here you have all the points in the middle of this right column vector, except in the first row you have this special, and in the last row you have that special expression. Okay, so these are from the end conditions specifying derivative vectors at the ends. Specifying derivative vectors at the ends. Specifying derivatives at p0 and pn. And that is very beautiful. Because now you get this unique answer in one shot. Boom. Click, 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 click. 2 vectors, 1 curve. And you invoke your linear system solver for tridiagonals, and you get it in an instant, right? Bye-bye.
The preceding program was brought to you by UC Davis on iTunes U. please visit us at itunes.ucdavis.edu.